Welcome to today's webinar, Basics Industrial Power Distribution Factory Automation for Non-Technical Professionals. My name is Ted Wodoslavsky. I'm the Director of Marketing and Market Communications for ABB Low Voltage Products. I'll be moderating today's webinar. Before I get started, I want to go over a few things. Today's webinar is being recorded. A link to the recording will be mailed to you following today's event. Feel free to forward the link to people you know who would benefit from the presentation. You may want to tweet about the webinar in your Twitter account. Before we get to our feature presentation, I want to introduce the 2013 ABB Automation and Power World event. This year's event will be held March 25th to 28th at the Orlando Convention Center in Orlando, Florida. Automation and Power World is a premier event for engineers and business leaders, designed so you can experience and learn the latest in automation and power technology and how it can benefit the profitability of your business. This mega event will include over 400 educational workshops on topics that are vital to the success of your business. Today's webinar will give you an example of the type of practical training you'll experience at the event. You can learn PDH and CEU credits and spend some valuable networking time with your peers. The event will also feature a Technology and Solutions Center with over 130,000 square feet of exhibits with nearly 100 tons of electrical gear and hundreds of experts ready to answer any of your questions and share the future of automation and power solutions. We're expecting over 4,000 attendees at this event, making it an excellent opportunity for face-to-face sharing of ideas and a chance to get reacquainted with old friends and colleagues. Here are some examples of educational workshops developed for all audiences, roles, industries, and experience levels. Be sure to bring your questions and get them answered by our expert panel of presenters. Here are some comments from past attendees. I'll be back at the end of today's presentation with more information about ABB Automation and Power World Conference. Now I'd like to introduce today's speaker. His name is Craig Endlid. He is the Mid-States District Manager for ABB Low Voltage Products and resides at Indianapolis, Indiana. I'm sure you'll enjoy Craig's presentation as he has a wealth of information to share with you today. Without further ado, I will now turn it over to Craig. Thank you.
All righty, Ted. Thank you very much. I appreciate that introduction. ABB's vision statement is shown here, and we are indeed an engineering company that helps our customers use electrical power efficiently to increase industrial productivity. Now, we are engineers serving engineers generally. However, engineers also interface with other professionals and vice versa. And to these folks, engineers and their buzzwords can be downright confusing. Yet, they need to relate to engineers and their day-to-day duties in order to get their jobs done. So, we will take some advice from Stephen Covey and his 7 Habits of Highly Effective People to begin with the end in mind. The end result of your participation in this webinar is you will understand the basic terms and concepts of industrial power distribution and factory automation. And therefore, you will better understand and relate to the manufacturing and the controls engineers that are at your company. Now, to show you what I mean, let's break the ice a little bit. This is a common piece of electrical gear that you might spot in a power substation. Now, what in the world are these weird-looking things called here? Well, I always thought they were called insulators, which is what they do, but the proper term is a bushing. Now let me explain it here. The curved shapes along the bushing create a longer path for an electrical arc to travel than a straight line shown by the wooden broomstick that's on the left here. Now both of these are insulators, but the bushing is a better one due to the greater arc travel distance. All right, now that we've got you brushed up and the ice broken here, let's start our orientation with a discussion of the basics of power distribution and circuit protection. Now I'd like you to bear with us a little bit as we cover a few basics that you probably learned in high school. There are 2 basic types of electrical current, AC or alternating current and DC or direct current. And you'll find both of these types in factories and in general in industry. Current is the amount of flow of electronics in a conductor. Current is measured in amperes or amps, and generally the higher the current, the higher the heat generated in the conductor. We have to remember that because heat is one kind of an enemy of industrial production, and we need to learn to deal with heat in our systems. Voltage is a measure of force of the electronics, or the electrons, I should say, in a conductor. And the higher the voltage, the higher the potential for the electrons to flow. Voltage is stepped up and stepped down in various stages as electricity is generated and distributed, in some cases over long distance, to various loads, such as an industrial load, a commercial load, or a residential load, shown in the bottom of this diagram. Shown here are the typical voltages at which it is created, then transmitted, and then received by the user. It's generally transmitted on 3 wires, as you can see in these towers here, and that means 3-phase electricity. And it's alternating from positive to negative at 60 hertz, meaning 60 cycles per second. Generally speaking, there are 3 broad types of electrical equipment that you'll find in industry. The first is electrical distribution equipment, consisting of things like transformers, bus duct, which is a duct that has bus bars inside, or metal bars for distributing power, distribution panels, circuit breakers, and even disconnects, which disconnect power to a motor or to a bank of switches. Second is electrical controls, and these are motors and then the associated controllers of those motors, sometimes found in control panels. Controls also are consisting of pilot devices, sensors, even a color graphic terminal called a human-machine interface, or HMI. And then finally, the third classification would be electronic instrumentation, things you might find on a panel, like a meter measuring voltage or amperage, or perhaps an indicator of the depth of a panel or a fluid in a tank. Electricity comes into a factory or a commercial building at what's known as a service entrance, shown on the left here. Switchgear is used to provide a means of disconnecting the power, but also protecting the facility from major faults, such as a short circuit. Frequently, there's a transformer that steps the voltage down to a panel board or a motor control center, shown in the center here. These panels have additional circuit protection on smaller circuits for loads such as lighting loads, heating and air conditioning equipment, maybe even plant floor machinery. Shown here is a one-line diagram depicting power distribution in a typical factory. But what I'd like you to notice is how it resembles an organization chart of levels of management in an organization. The concept is similar in that decisions are pushed down to the lowest level. A circuit breaker can trip to protect one motor that may be overloaded, isolating just that motor, and hence not taking down the operation of the whole facility by tripping the main incoming circuit breaker at the very top of the circuit. Engineers must size and select short circuit protection at all levels to coordinate their systems so that electrical faults or short circuits are cleared at the very lowest level. This helps to maximize the productivity of the remainder of the facility. There are 2 types of devices that protect circuitry. Fuses are the simplest form, and they are lower in cost, but they are consumable. So you blow a fuse, you do need to replace it. The other form of circuit protection is called a circuit breaker. It is resettable, so it is not consumed like a fuse, but it does cost more because it's a more complex machine. These provide thermomagnetic protection, meaning that they sense both excessive heat being generated downstream, and they also recognize excessive current being generated that creates a magnetic surge. In both cases, the circuit breaker will trip to protect the equipment downstream. Circuit breakers are found in 3 main types. A miniature circuit breaker on the left here is typically mounted on a steel rail within an electrical enclosure. A molded case circuit breaker is screwed onto a backplate in an enclosure, and that's shown in the upper right. And then finally, an air circuit breaker is found in higher current ranges, typically in incoming switchgear, and it's usually either rack-mounted or screw-mounted into the panel of basically a box of switchgear. Now, there's other types of circuit protection that counteract temporary surges due to lightning strikes, for example. Shown here are metal oxide varistors, or MOVs, which channel a voltage spike to ground, thus protecting personnel and equipment. A power strip with surge protection for your home computer, for example, uses these MOVs. Now that we've seen how electricity is distributed and protected, let's take a look now at how it's controlled as it's used in industry. When we talk about industry and production, we're talking about work being done and energy being captured and utilized. The way we do work has varied over the years, and technology has come a long way. The electric motor is the workhorse of industry, and as a matter of fact, 40% of the electricity generated in the United States is used by electric motors. Now, there's two basic types, AC and DC. The most prevalent is the AC motor. Its horsepower, or its force, or its strength, ranges from fractions of a horsepower to thousands of horsepower. The typical motor operates at 460 volts, three-phase current, and has a fixed speed of 1,750 revolutions per minute, or RPM. Hey folks, I promise not too much math on this webinar, but I wanted to show this simple equation for the speed of a typical AC motor. And notice that frequency does not ever change. Incoming power is always at 60 hertz when it comes into the building. The number of poles does not change since they're built into the motor, and 120 there in the numerator is a constant. Therefore, speed of the motor is always a constant 1,800 RPM. Now actually, by design, the motor slips a little bit, and that helps create the magnetic field in the motor. So in reality, a typical AC motor has a fixed speed of 1,750 revolutions per minute. Now, what if I have to vary the speed of a fan or a conveyor? I want to run it slow, medium, fast. Well, normally with an AC motor, we'll have some sort of a transmission or a belt or pulley type arrangement where we vary that speed mechanically. A little bit later in our conversation, we'll talk about how we can electronically alter the speed of that electric motor. All right. In our factories, we perform work on materials. Now, the workhorse is the electric motor, obviously, and its fuel is electricity. We must control the work that we're doing. We must harness and control this electricity. So what it comes down to is a science that we call electrical controls, or even automation controls. And in your place of business, we have to regulate or control these motors. And in many cases, that is done through the engineering work of either control engineers, automation engineers, or maybe even manufacturing engineers that you work with at your place of business. Now, what do we mean by control? Well, let's look at a definition of control from the dictionary. Basically, to regulate is the power or the authority to guide or manage, in this instance, a machine or a process. Here's a dictionary definition of automation dating back to around 1948. And I particularly like definition number 2, automatically controlled operation of an apparatus, process, or system by either mechanical or electronic devices that take the place of human organs of observation, decision, and effort. Now, let's remember that, observation, decision, and effort, because that, in effect, is what our electromechanical automation systems are doing. In manufacturing, there are multiple forms of control, and they're summarized here. Sequential control, regulatory control, motion control, and coordinated speed control. Now, what's interesting is that all 4 of these types of control are found in these 3 basic forms of manufacturing. You are engaged either in batch processing or batch manufacturing, continuous manufacturing, such as perhaps a processing plant like a refinery, or discrete parts manufacturing, maybe an appliance manufacturing plant, a widget plant, so to speak. Again, all 4 types of control are found distributed among the 3 types of manufacturing that are shown here. Now, let's start with sequential control. Here's an example of a box on a conveyor. A photo eye observes the conveyor and trips off the motor starter when the box breaks the beam. Notice the closed loop here, observation, decision, and effort. Sequential control consists of typically hundreds of these observations, decisions, and outputs. Sensors and controllers perform timing cycles, the counting of parts, the sequencing of manufacturing steps, and the interlocking of systems so that parts get produced at the proper sequence and at the proper speed. Sequential control is typically found in discrete parts manufacturing, or essentially the making of widgets. Here's a typical regulatory control example. Here we're cooking a batch of soup or chemicals and need to regulate the temperature. Observation is done by a temperature probe that connects to what we call a summing junction, which compares the actual temperature to our desired temperature, or set point. If there's a difference, it opens a gas valve to raise that temperature. Here again, in more or less a closed-loop fashion, we see observation, decision, and effort. Regulatory control is used to regulate temperature, pressure levels, flow rates, and speed. And these factors can affect the products that we produce in terms of viscosity, acidity, temperature, control, taste, and so on. Here we see a video of a cement kiln where our control system is regulating both the temperature and the speed of rotation of that kiln. Now, for very accurate regulation, the summing junction typically has some computational capability. We call this a PID controller, and PID stands for proportional, integral, and derivative. Yep, you guessed it, calculus. Now, here's why you need calculus. Let's say you suddenly crank up a set point from 0 to 100%, shown by the light blue line. The system will open the gas valve at full bore and heat the chemicals as fast as possible. But there is a possibility, based upon the design of the system, that once the temperature crosses the set point line, there will be a delay in closing that valve, and thus overshoot, as shown by the dark blue and the green lines. We want a system that's smart enough to start backing down the gas valve when we come close to set point, as shown by the desired red line. Hence, we design smarts into the controller, and we can turn on, turn off, and tune these three parameters to match the unique physical characteristics of the application. For proportional control, the valve will open in proportion to the set point versus the actual temperature difference. For integral control, the controller will add up all the changes at set point over time. And then finally, for derivative control, the valve will open and close the rate of change in the set point versus the actual temperature. So this makes for smarter control. Now, basically, this is the calculation, basically the classic control algorithm in calculus. I won't bore you with the details, but this is the last calculus I promised to show you in our presentation today. Now, PID controllers take the shape and form of what we call single-loop controllers, as shown here. You'll see these all over a typical factory, controlling kilns, ovens, fluid levels, and much, much more. In a batch processing plant, such as a refinery or a corn processing plant, there may be hundreds or even thousands of PID loops that need to be controlled. A distributed control system, or DCS, is a computer-based system that connects to and controls all of these loops in one system, rather than individual loop controllers. Sophisticated color graphic stations depict the process being controlled and show production and process control data along the way. On to motion control, and this is a motion control loop, typically also called servo control. Now, it's similar to PID control, but in this instance, it is to control positioning instead of regulating temperature. A ball screw rotates, moving a table in a lateral motion. A device called an encoder, shown on the right, observes the positions of the table and reports it to a servo controller, which commands the servo motor to move the table to a set point position. Once again, closed loop control. Motion control, or servo control, is typically used in three-coordinate space for such applications as material handling, metal cutting, packaging, and robotics. These systems are extremely precise. In machining of metal parts, it's not uncommon to cut metal to the 10,000th of an inch. Coordinated speed control involves the very close regulation of the speed of multiple motors. there are many motors driving the rollers in the paper application that's shown here. And if any motor gets out of synchronization, the paper will rip, thus ruining the product. Speed control is found in the metals, paper, and other continuous process type of industries. All right, today's manufacturing involves a mix of differing types of control that we've discussed. And shown here is a relative distribution of these types, with discrete or sequential control probably being the most prevalent in industry, as shown by the pie chart. Now that we know the types of control found in industry and the types of industries or manufacturing processes, let's discuss the equipment and the systems that provide this control. Here we see a variety of machine types found in manufacturing, such as mixers, conveyors, and automatic assembly machines. To automate or control these machines, we start with electrical devices, such as motor starters and push buttons. These are wired together into systems, such as a PLC or programmable logic controller system, to operate a given machine. These systems are sometimes networked together, and they report on production. And we program the controls for a given application, hence they become applied systems, such as a paper machine control system. Software is used for the design, for operation, for maintenance of these systems, and it's used to commission and operate the applied system. Here we see a very typical electrical control panel consisting of a rugged steel enclosure and a back panel upon which are mounted electrical control devices that are interwired to form a system. Wires exit the control box and connect it to operator stations and also to sensors and actuators that are mounted on the machine that we're controlling. Now let's talk for a moment about the sensors on the machine. You can buy a good old selector switch from Radio Shack, as you see here, for a few bucks, and it'll do what's needed on the machine, well, for about a day or two. You see, electrical controls are what we call factory hardened, meaning that they're designed to be heavy duty and rugged to survive a nasty, noisy, and dirty shop floor. The standards by which these devices are designed are shown here. NEMA and UL are North American standards bodies, and the IEC stands for International Electrotechnical Commission, and that's the European standard. Okay. Now let's take a look and see what a typical building block would be of control systems. Alrighty? First of all, we start with the basic building blocks of a typical control system: input, logic, and output. Inputs can be push buttons, limit switches, pressure switches. That's all shown with the symbols on the left. Outputs can be motor starters, solenoids or actuators, pilot lights, things like that. And the logic block typically consists of control relays and timers which establish the sequence of action through which the use of basic logic is done. And then finally outputs, the actuators that are shown on the right. In this case, a motor starter or device starting an electric motor, or the symbol for a solenoid, which is an actuator. Let's bring back our basic definition of control and point out that inputs provide the observation of our systems, logic devices provide the decisions, and then the output devices provide the outputs to the system. Now, a very typical example of an input device would be a push button station as shown here. 1 meaning on, 0 or red meaning off. Notice that there is an air gap on this symbol for the start push button. This is designed to be a circuit symbol, and power is designed to be flowing from left to right through these wires or these lines that are shown on the symbol. You press the start button down, you connect the circuit, and you start an electric motor or a circuit. Conversely, look at the stop button symbology, and you notice that it's a normally closed device. In other words, it's conducting current in its off state or its shelf state. If I press the button down, I will open up this circuit, hence I discontinue power flow through the device. A limit switches is a form of another input device. It's really basically a switch. However, it's built in a cast body, cast aluminum body, and if a box or some sort of object trips this lever, it will open or close the switch. So we're doing basic product detection with a limit switch. Here we see symbols for normally open of a limit switch and normally closed for a limit switch as well. Okay, Photo eyes and proximity sensors provide the absence and presence detection of a limit switch, but they're no touch by design. A product either breaks a light beam, or in the case of a proximity device, it'll detect a piece of metal coming within a few millimeters of the sensing head of the prox, and that's the little cylinder device shown in the bottom right. No touch means less mechanical wear, and therefore less machine downtime. Another form of an input would be what we call analog signals or digital signals. In this case, these are temperature probes. An analog signal varies between plus and minus 10 volts negative current or positive 10 volts DC current. It will vary in proportion to the temperature that it's measuring, so it can measure a range of a particular parameter. A digital signal is either on and off, like a limit switch tripping or a push button being switched off or on. Typically, digital signals in control systems are 24 volts DC in Europe or 120 volts AC in the United States. A form of output, very popular, would be pilot lights or tower lights that are shown here. And you can see the circuit symbol showing the color of the lens by the letter designation in the center. You can see the bit of a glow here, and this is the typical symbol of a pilot light, which is a typical output. Now, another very popular output in our control systems would be what we call a contactor. And this is more or less the form of a relay, but it controls an electric motor. The electric motor, the power to it flows through this power circuit on the front here, and typically this is 460 volts, three-phase AC current. There's a series of contacts in the front here that open or close to turn the motor off and on. In the back of the contactor would be an electromagnet that's powered up through a control circuit that's 120 volts AC in nature. A push button would control this. So basically we're isolating a human touch being at the push button level from the 460 volts, which is more hazardous at this level here. So one of the functions of a contactor is to isolate a human operator from a higher voltage motor circuit. Here we see a contactor de-energized. The electromagnet is not conducting electricity or not receiving electricity, hence we're not conducting power to the motor. We energize the contactor through putting 120 volts across the coil. We see that the switch is closed and we're conducting power to the electric motor. Now, a contactor plus what we call an overload relay, which is the bottom device here, combined together form what we call a motor starter. So a motor starter not only starts and stops the electric motor, but it protects it by sensing overcurrent situations. Inside this overload are a series of what we call heater elements. They're measuring the current. You can see them in series here with the three phases of power feeding into the electric motor. If we lock the rotor, put a wrench in and goof up the rotation of that electric motor, that rotor may freeze shut and basically forming a short circuit. So current will flow to infinity unless we stop that electric motor. We sense the heat through these heater elements, which are mechanically linked to these contacts that we see here. It'll open up power to the power circuit to the electric motor, thus protecting the motor. Again, overload relay plus contactor added together equals a motor starter. Now, we mentioned at the outset that 60 hertz electricity is prevalent and that an AC motor is a 60 hertz machine. Well, not quite. In recent years, there's a new technology out called a variable speed AC motor drive. What happens is this is an electronic box wherein we will feed three-phase 60 hertz electricity at 460 volts into what's known as the AC drive. The inverter section of the AC drive takes in alternating current and creates DC. Then power transistors that are mounted inside the box are fired by a control board, and it literally recreates alternating current from DC, but it does so at a varying frequency. There's literally a potentiometer or a dial on this controller, and I can send 0 to 60 hertz, and in some cases 90 hertz out to this electric motor. So what used to be a fixed speed machine can now be varied in speed. Thus, it's a very economical solution because I'm eliminating gears, pulleys, transmissions, And mechanical gizmos that used to be necessary to vary the speed of my output now I simply vary the frequency into the electric motor. These are gaining terrific popularity, called a variable speed AC motor drive. Alrighty, what about the logic? We've got observation of inputs. We have outputs that are our efforts. We need a control system that processes those inputs via logic to create a desired pattern of our outputs. Let's do some logic here. This is a fairly simple, what we call relay ladder diagram. It's a circuit diagram, and electricity is going to want to flow from line 1 to line 2, and we form rungs of logic. So we can see here a simple push button, and if I press the push button and hold it, I will conduct power to the red pilot light. This is a very simple if circuit. If push button pressed, red light glows. Now, electromechanical relays are like the contactors we talked about, but they don't start and stop electric motors. They have normally open or normally closed contacts, and they have a coil. So when I energize the coil of the relay, I can either open or close contacts at will. And as I wire these in patterns, I can form different patterns of what we call Boolean logic. Now, sometimes a relay also has a delay built in, and that's called a timer. Or another form of a relay might count the number of pulses, or the number of times I close its coil, and stores those numbers. That's called a counter, or it's another form of a relay that's counting a production. Now, let's look at these various forms of logic, and logic is shown here. If push button 1, controlling this relay, and limit switch 1, controlling this relay, and pressure switch 1 are closed, you'll see in series those contacts associated with those coils are wired in series. So my AND logic says this and that will turn on that. The other form of logic is OR logic. This button, this limit switch, this pressure switch, any of them, this one or that one close, I'm going to close control relay number 4. There's even something called NOT logic. If limit switch 1 closes and fires the control relay number 1, the normally closed contact is going to open up, turning off the red pilot light. Now what's interesting is that electricians will take hundreds of these devices and interwire them to form some fairly complex patterns of Boolean logic. And you can see here, here's a simple relay ladder diagram that can actually get quite complex should you have a large control system or a large machine that you're wishing to control. Now you'll see here also a nomenclature where we're numbering the rungs, and we're allowing an electrician to go and troubleshoot a system should there be a problem with one of these timers or one of these relays. Now, there is a new form, a relatively new form of logic, and actually it dates back to the late 80s, early 1990s, called a programmable logic controller system. It's a solid-state device, more or less a computer in an industrial package, and it does not take the place of the inputs on the machine nor the outputs, but it does take the place of logic, or hundreds of relays in some cases. What's good about a programmable logic controller is you still wire up to your standard input devices, and you wire it into what's known as an input section, which isolates the noise and the clackety-clack that's coming from the machine and keeps it isolated from a central processing unit, which is indeed a microprocessor that's running a software program that emulates the ladder diagram logic that you would see in a hardwired system. Then this central processing unit communicates to output hardware, which also has lights that show an on-off status of each of the outputs that are wired into the system. What's nice about moving from relays to a central processing unit like this is that you can do some fairly in-depth computer-based functions, not only time delays and logic functions, but now shift registers, diagnostics, documentation, analog to digital and digital to analog conversions, and so on and so forth. So the system can get fairly intuitive and hook up to a variety of different types of equipment. This is called a programmable logic controller, and it's very prevalent in industry. Alrighty, and the good news about a programmable logic controller is that you program it not in Fortran, BASIC, or COBOL, or some computer language. You actually plug in a video terminal and you type out or create a graphic ladder diagram, as if you were wiring a panel of relays. What's nice about that is that the electrician that used to wire up relays or troubleshoot using a print can now go to and understand the screen without being trained in the computer language. It's a wonderful example of being able to provide ease of troubleshooting and ease of programming in a shop floor type of language. Alrighty, now we've talked about the basic building blocks. These systems can be integrated to form what we call computer integrated manufacturing. What we mean by that is basically levels of computing that are found in the modern manufacturing enterprise. Shop floor automation systems doing the three types, batch control, continuous control, or discrete control. These are typically performed through the programmable logic controllers and the variable speed motor drives that we discussed earlier. But these can be networked together and report to manufacturing execution systems. These are computer systems that do manufacturing operations management, controlling what's going on the shop floor. Then these computer systems can use networks to report up to enterprise resource planning systems. That's planning the overall enterprise logistics, forming kind of a managerial pecking order, if you will, where we have control, reporting, and then overall supervision. The way it's done is through the integration of control networks, device networks, and Ethernet in these systems. And shown in this diagram are programmable logic controllers, in this case a discrete control loop that's running a machine, networked together and talking to its peer, which might be running another machine, feeding parts among each other, and then reporting to its supervisory control system, which in turn reports up to an overall plant supervisory system, such as an ERP system. Now, whether it's factory automation control with PLCs or process automation through DCS systems, which we talked about earlier, the architecture, the input-output structure, the CPUs are very, very similar. However, a DCS system and process automation typically is more definite purpose and tuned to a process. Hence, it's more complex. But generally speaking, you'll see the same kind of architecture of systems between both factory automation or discrete manufacturing and process automation. And that's it for presenting to you both the power distribution and the electrical control side of an enterprise. I'll now turn it over to Ted to close our presentation. Ted?
Thanks, Craig. I want to close today's event with some additional information about the 2013 Automation and Power World Conference being held March 25th to 28th in Orlando, Florida. The content you heard today in today's webinar is just an example of the training sessions that will be offered at the conference in March, or actually just in a few weeks. Here are some statistics on the powerful training events that we are assembling. We are providing a number of different registration options for this year's event. You can register for all 3 days, or for select days at some very reasonable rates. There is also a free one-day courtesy registration, especially designed for spouses or special guests, or anyone who would like to stop by and see the Technology and Solution Center. You know, we have top 10 reasons to attend. If there aren't enough reasons to attend this year's event, you can take a look at these 10 reasons why you don't want to miss. What we don't have here is that it's actually in Orlando, which is a beautiful place to be in March. Myself, I'm sitting in Michigan right now, and it's snowing once again, so being in Orlando in about a week is a pretty tempting proposition. Here's the URL for registering for the event, abb.com/apworld. At this URL, you will also find some links to the conference brochure and additional free webinars, like the one you saw today. That we're offering, and we offered some in February, and also offering them here in March. We look forward to seeing you at the conference next week. Thank you for attending today's webinar. When you close the screen, you will see a short survey of today's event. We appreciate your feedback and comments. Thank you, and have yourself a great day.